Electrical circuits can be one of the more challenging topics in the ESAT and the PAT, with questions tending to place a far greater emphasis on problem solving and the various subtleties that can arise when applying the equations to more complicated cases. One of the equations which tend to cause the most confusion is V equals IR. In this video, we're going to explore the relationship of the equation V equals IR to the famous Ohm's law, as well as the way we can apply V equals IR both to individual components as well as the circuit at large. Some equations in physics follow from a mathematical derivation or proof, while others are true by definition of the quantities involved. V equals IR falls into the latter camp. Recall that resistance is a way of measuring the opposition to the flow of current in a circuit, where in particular we define 1 ohm as the resistance such that a potential difference of 1 volt will induce a flow of current equal to 1 amp. So we know that current will tend to flow along a potential difference, just as water tends to flow downhill, and a resistance of 1 ohm is such that 1 volt will induce a flow of 1 amp. So that means one way of defining resistance is that it is the potential difference needed per unit of current that you want to flow. So it's how many volts you need per amps you want to flow, to put that in terms of SI units. So that means that by definition of resistance, not through any mathematical derivation, but purely by definition, we have that resistance R is equal to V divided by I, potential difference divided by current, and that equation straightforwardly rearranges to give V equals IR. So this is not some deep statement about electrical circuits that follows from a mathematical derivation. It's simply another way of posing the definition of resistance, and therefore it is always true for every component. A common misconception is that the equation V equals IR is the same thing as Ohm's law. However, this is not quite the case. V equals IR applies for all components, whereas Ohm's law is a special version of the relation which holds for certain components referred to as ohmic. Ohm's law states that for certain components referred to as ohmic, for example, a resistor at a constant temperature, V equals IR holds with R being constant. So what is really important to emphasize is that even for a non-ohmic component, for example, a filament lamp, the relationship V equals IR still holds for that component, but the reason Ohm's law breaks down is because R is no longer constant. For example, for a filament lamp, R will increase as we increase V or I because the lamp will get hotter. So Ohm's law is not always true because it comes with an additional constraint that the resistance itself is not changing. So if we have an ohmic component, for example, as I said, a resistor at constant temperature, the fact that V equals IR with a constant value of R means that if I plot the IV graph, I'm going to have a straight line through the origin. Moreover, if as standard we plot potential difference on the x-axis and current on the y-axis, the gradient of my line is obviously going to be the same as whichever point I use to calculate the gradient from the origin. It's going to be the current at that point divided by the potential difference at that point. So whichever point I use to compare with the origin using rise over run, I'm going to get the same value because the gradient's the same everywhere. So that means not only do we have a straight line through the origin, but it's specifically a straight line through the origin with gradient I over V, which of course is the reciprocal of the resistance, 1 over the resistance. Now, if we have something like a filament lamp, where the resistance is not constant, the graph will no longer be a straight line. It was a straight line for an ohmic component because we had V equals IR with R a constant, but now R itself will be some complicated function. You can view it as a function of I or a function of V, depending on what perspective you want to take. So we can get curvier shapes. Now, it's really important to remember that although you can define the gradient at a point on the curve by taking the gradient of the tangent, the gradient no longer corresponds to anything with a simple physical intuition. So it's certainly not the case that if I take the gradient of the tangent line at a particular value of v, that tells me the resistance or the reciprocal of the resistance at that particular value of v. The gradient at each point ceases to be particularly important. However, if you want to work out the resistance for a particular value of v, all you need to do is go to that particular point and do the value of v divided by the value of I, because the relationship v equals IR still holds. Since v equals IR relates the three most important circuit quantities, potential difference, current, and resistance, it provides a vital tool for determining unknowns. We can apply it across any component in the circuit. So if we know any two of the potential difference across the component, the current through the component, and the resistance of the component, we can use the equation to pin down the value of the third unknown. Crucially, we can also use v equals IR on the overall circuit to figure out something about the current flowing through the cell. And this can be an absolutely indispensable tool for more challenging circuit configurations. We can apply v equals IR to any component in the circuit we wish, and it tells us that the potential difference across that component is equal to the current flowing through that component times the resistance of that component. Now, this is already very valuable, because if we know 2 out of these 3 quantities, we can now use the equation to pin down the third unknown. However, especially in more challenging problems, it's also often very useful to apply v equals IR to the circuit itself. So we'll use the idea of a total resistive load to apply this equation to the circuit at large, and this is especially useful because it lets us figure out what is the current which is actually being drawn from the cell. So in other words, what is the current flowing through the cell? Now, this current might split up in various ways across parallel branches if the circuit's complicated, but knowing what the unsplit current is that flows through the cell already gets you most of the way, in the majority of problems, towards a solution. So the idea is we have this principle of a total resistive load. So if we have lots of components spread around the circuit, maybe some in series, some in parallel, we have rules for the addition of series to figure out the total effect that all of these components have. And then the idea is, in terms of the opposition to the flow of current, we can imagine replacing all of these components, perhaps in a complicated arrangement, with a single component whose resistance is the total resistive load. And then when we talk about using v equals IR on the circuit, what we're really doing is we're using v equals IR on this imaginary component which takes everything in the circuit into account. So the rules are very simple. We won't go through their derivation here, although we may touch on this in a future video. For now, let's just remind ourselves. For components connected in series, we simply add the resistances. So if I have n resistors with resistances R1 to Rn, all connected in series, that's equivalent to a single resistor whose resistance is just the sum of those resistances. So in series, we just add things naively. And it's similar in parallel, but everything gets reciprocated. So if I have n resistors connected up in parallel, then that's equivalent to one component with resistance RT for R total, where 1 over RT is 1 over R1 plus 1 over R2 through to plus 1 over Rn. So it's still a simple addition rule, but everything becomes 1 over. And of course, once I know 1 over RT, I can do 1 over that to get RT. So once we've used these rules, we can imagine replacing all of the components in the circuit with a single effective resistor, whose resistance we've worked out using these rules, and then we can apply v equals IR on that imaginary component. So let's work through a simple example. Suppose we have this circuit. So we have a cell with potential difference 8 volts, and then we've got some parallel branches. So on this branch, we've got a 2 ohm and 1 ohm resistor connected in series. So using the simple addition rule, that's going to be equivalent to a single 3 ohm resistor. So I've effectively got a 3 ohm resistor in parallel with a 3 ohm resistor. So using the rule for parallel addition, 1 over the total resistive load is a third plus a third. So that's 2/3, and therefore reciprocating, the total resistive load is 1.5 ohms. So now we imagine having a circuit where instead of all those resistors spread around, we've got a single resistor whose resistance is this total resistive load, 1.5 ohms. Now, let's think about what we learn from V equals IR on this imaginary component. First of all, by Kirchhoff's voltage law, the potential difference across that component is 8 volts. So that's because Kirchhoff's voltage law says that around any closed loop of the circuit, the sum of the potentials gained across cells will match the sum of potentials dropped across components. I've just got one cell and one effective imaginary component. So the potential difference across this is the same as for the cell. It's going to be 8 volts. The current, because everything's in series in this imaginary construction, the current through this component is the same as the current that flows through the cell. So of course, in the real circuit, that current I splits up on these branches. So the current that I'm going to find, the I, is the unsplit current that was flowing through that cell. And so by using the equation V equals IR, I see that 8 is 1.5 I, and so I is going to be essentially 16/3, or 5.3 recurring amps. So now I know what the current is that flows through here. We can use simple principles to figure out how that current splits along the parallel branches, and effectively anything we want to figure out about the circuit will then be straightforwards. So when we talk about V equals IR on the circuit for these simple setups, say with a single cell, although we'll talk about multi-cell setups in a moment, the idea is that the potential difference of the cell, because that's going to be the same as the potential difference across your effective component, equals the unsplit current which flows through the cell. So that might split elsewhere in the circuit, but that's going to be what flows through our imaginary effective component times the total resistive load. So this equation is then very valuable for getting to grips with more complicated circuit setups. The application of V equals IR to a circuit does become slightly more complicated if we don't have a single cell. So for example, we might have some cells connected in series, or we may have some cells connected in parallel. For simple cases, we can still use V equals IR to learn something from these configurations. So consider, for example, if in our circuit we have multiple cells connected in series. We can undertake the same analysis as far as the components are concerned. We can find the total resistive load. And now it's as if we have our imaginary effective resistor in series with the cells, which are themselves in series with each other. So the analysis proceeds essentially identically. The current is the same through each cell as through the component because everything's in series in this arrangement, so there's no splitting of current. The total resistive load is the resistance of my imaginary component, and the only difference is that now if I try to figure out the potential difference across my imaginary component, Kirchhoff's voltage law applied to this closed loop around the circuit now tells me that the potential dropped across this guy is the same as the sum of the potential differences across the cells. So I can still use V equals IR on the circuit, so to speak, but now V is not going to be the potential difference of an individual cell, but rather 8 plus 6 plus 7. Now, of course, another way to think of this is that really when we connect cells in series, it is always really as if we're using a single cell whose potential difference is their sum. Things are slightly more complicated if we have identical cells in parallel. So for ESAT and PAT, we'll only really be thinking about identical cells connected in this way, unless they're spread around a circuit in a more complicated way with components in between. We'll look at that actually later on in this video. But consider we have identical cells connected in parallel. So we've got two 6-volt cells, and then again, for all the components, we've identified the effective imaginary resistor, which has the same effect. So there's now more subtlety, for example, with current. So there is the current I, which flows through my imaginary component, And notice that obviously the current will split by symmetry equally across the two cells, but each individual cell is only receiving a current of I by 2. So the I in V equals IR, the I flowing through my imaginary effective component, is no longer the current flowing through each cell. It's now, if you like, the total current flowing through the two cells. In terms of potential difference, remember Kirchhoff's voltage law applies to a closed loop around the circuit. So this is one closed loop. Obviously, another closed loop that we could, in theory, take is the one that goes that way round. Each closed loop only crosses one of the cells. So that means that the potential difference across my effective imaginary component is 6, not 12, the potential difference of just one of the cells. And R is clearly still R tot. So for this configuration, if I use V equals IR on the circuit, so on my effective total resistor, I get 6. The potential difference of one of the cells is I, the unsplit current that flows through here, of which half flows through each cell, times R tot. So it's not difficult. It's best to actually draw it out if you're at all confused and think about actually putting in this imaginary effective resistor. Now we can have more complicated configurations. So for example, here's a setup from NSAA 2023 section 2, which is much more complicated. We've got cells dotted around the circuit with components between them. So in these more complicated configurations, it's best not to attempt a V equals IR on the circuit analysis and instead return to first principles using Kirchhoff's current and voltage laws. So we won't explore that in this video, but we may turn to it in a future video. V equals IR is one of the most important tools you have at your disposal for dealing with more complicated circuit setups. And with a good understanding of the subtleties, you'll be well on your way to being able to tackle even the hardest problems encountered on admissions tests. I hope you found this overview of V equals IR helpful. If you're interested in more videos on useful ideas from maths and physics relevant to the various admissions tests, do remember to subscribe. And if you're interested in exploring more structured support for your admissions test preparation, do visit our website, linked in the description, where you can read about the details of the various programs we offer. Thanks for watching.